In this video, we will learn about improper integrals. You should have this handout printed off sitting in front of you. You should have some extra note paper off to the side to write down the examples, and then we'll be ready to begin. So we want to understand what improper integrals are and figure out how to solve them. Let's review a little bit about integrals. Definite integrals are an important concept in calculus, and they correspond to areas under curves. So if we draw out a generic example here, let's just imagine some random looking function f of x, and let's say we take the area from a to b. The definite integral from a to b of this function f of x is just the area between the curve and the x-axis. So this would be some area that would be a positive area, and then we have some area down here that would be a negative area, and the definite integral takes both of these areas into account. So big concept in calculus, definite integrals correspond to areas under curves. How do we find definite integrals? How do we compute these areas? Well, we compute them using the fundamental theorem of calculus, part 2. Here's the basic statement for fundamental theorem of calculus, part 2. It says in order to find a definite integral, we must first find the antiderivative, capital F, then we plug in the upper limit, plug in the lower limit, take the difference, and that will give us the value of the area under the curve. This is the statement of the fundamental theorem of calculus, part 2. Now, we're used to seeing this statement, but sometimes we might forget about the necessary conditions involved. There are conditions that must be met in order for us to use this theorem. The conditions are, we must have a continuous function on a closed interval. So we start with a continuous function f on the closed interval from a to b, and then if we find an antiderivative, capital F, then we can use this expression. So what happens if we want to integrate over an infinite interval? What if we have a function that maybe looks something like this, and we want to add up area starting at some value and going all the way off to infinity? Maybe that has a finite sum. Or what if we have a discontinuity within the interval? Well, if that happens, then automatically we have violated the conditions for the fundamental theorem. So as stated, we can't just apply this fundamental theorem of calculus. Sometimes there is a way to deal with these integrals. These are called improper integrals. We have two main types of improper integrals. Integrals where we're trying to integrate over an infinite interval, or when we have a discontinuity over the interval integration. These are called type 1 and type 2. It's not really important that we understand which one's which. It's just important that we understand that we have two different types. So how do we handle these improper integrals? Well, the first step is to identify problematic limits of integration. These will usually be plus or minus infinity, or they will be a place at which the function has a discontinuity. We simply replace these problematic limits with variable names. We'll just call them a or b or whatever. The next step is to take the limit of the integral as the variables from the last step approach their true value. And then step 3, we evaluate the integral, and then we solve the limit to determine whether the original integral converges or whether it diverges. If the limit exists, then the integral converges. If the limit does not exist, we say the integral diverges. Let's try an example. This is example 1 from the back of the handout. We have the integral of 1 divided by x squared from -2 to +2. Now, before I show you the correct solution, I just want to illustrate a naive approach. Let me show you the incorrect attempted solution at this. So don't write this down, but just watch. This will feel rather intuitive probably, but it's the incorrect method. Well, we're tempted just to find antiderivatives. So one thing that I could do, and this is correct, I could replace the 1 over x squared with x to the -2. I'm just rewriting that 1 over x squared. So this is okay, but I'm tempted just to find antiderivatives right away. So the antiderivative of x to the -2 is x to the -1 divided by -1, or I could write that as -1 over x. I'm integrating from -2 to 2. So I've got my antiderivative, and now I'm tempted to plug in my limits from -2 to +2. So I would start by plugging in the upper limit, -1 over 2, minus -1 over -2. Using the fundamental theorem, that's the expression that we get. I have a minus over a minus, that's a plus. So -1/2 minus another 1/2 is a -1. And that's the answer that we get. Now, at this point, things seem okay. We got an answer, we got -1, and we don't really see any problems here. So did we do this correctly? Is the answer -1? Well, no, it is not. -1 is an incorrect answer. Let's visualize this in Desmos. Remember, we're finding the area under the curve of 1 over x squared from -2 to 2, and using this incorrect method, I got an answer of -1. Let's look at the graph and see if this makes sense. Here is the graph of 1 divided by x squared. If we integrate from -2 to +2, the region looks like that. This region is all above the x-axis, and area above the x-axis should be positive. But in the example that we just worked through, we got -1 as the area. There's a problem here. Our approach of solving that definite integral didn't work. So let's take a look at the correct method. Here's example 1 again, and we need to remember that we have a discontinuity when x equals 0. Because of that, this is an improper integral. So how do I deal with that discontinuity? Well, I'm going to split apart the integral into 2. On the one hand, I'll have the integral from -2 to 0, and then I'll have the integral from 0 to +2. The reason I split the integral apart this way is so that I can identify the problematic limit. 0 is the place where we have the discontinuity. So 0 is the problematic limit. Now I'm just going to focus on one of these two integrals. We're going to see that one of the integrals diverges, and because of that, the whole thing diverges. So for now, let's just focus on this integral from 0 to 2. The problematic limit is the 0. That's where the function is undefined. So I'm going to replace that with a variable. I'm just going to say the integral from a to 2. And now I'll take the limit as a approaches the true value of 0. Now, since we're integrating from 0 to 2, we only have positive values of x here. So I can think of a approaching 0 from the positive side. This is actually a one-sided limit. All right, now, for the time being, I forget about the limit, and I just solve the integral. I keep the limit notation, but I just focus on the integral. I can solve this integral as normal now. I can take the antiderivative of 1 over x squared. That's -1 over x. And now I'm using fundamental theorem of calculus for this expression here. So I plug in the 2, plug in the a, take the difference. I keep the limit notation. And I have -1/2 minus -1 over a. Minus a minus is a plus, and this is what I have. Now, the -1/2 can come out from the limit. That's just a constant. And then I'm adding the limit as a approaches 0 from the right of 1 divided by a. As a gets closer to 0, 1 divided by a becomes larger and larger. And we could illustrate this with a small graph if we wanted to. 1 over a looks something like this. Here's the a-axis. As a approaches 0 from the positive direction, the y values of the function go to infinity. So this limit is positive infinity. So I have 1/2 plus infinity. That's infinity. So this would tell me that this integral does not converge to a value. It is an infinite integral, if you will. So I say the integral does not converge. Let's take a look at example 2. So here we have our different integrals, and for each one of these we want to write down why the integral is improper. Let's do that for the first one while we're here. This is improper because there is a discontinuity at x equals 0. The second integral is improper because of the infinity. So we don't have a discontinuity here. The only issue is this infinite limit of integration. So the reason that example 2 is improper is because we have an infinite limit of integration. Let's work through example 2. Notice that we have the same function that we had from example 1, but just because the integral from -2 to +2 didn't converge, that doesn't imply that this integral won't converge. Let's work through the procedure. We replace the problematic limit with a variable name. Let's just call that b. So we're integrating from 1 to b, 1 over x squared dx, and then out front we take the limit as b approaches its true value, infinity. For the time being, we forget about the limit and we just focus on taking this integral. We'll keep the limit notation, but we'll just focus on the integral. Antiderivative of 1 over x squared, once again, is -1 over x, and we integrate from 1 to b. Plug in a b, so -1 over b, minus -1 over 1. Again, minus a minus becomes a plus. And this plus 1 is not affected by the limit, so I can just take that out from the limit. So I have 1 plus the limit as b approaches infinity of 1 over b. What happens to this limit? Well, as b becomes larger, I'm dividing by larger and larger numbers. Dividing by larger and larger numbers results in a smaller and smaller quantity. So this goes to 0. So I have 1 plus 0, so my answer is 1. We would say the integral converges to 1. Let's take a look at this in Desmos once again. So here we have the same function, 1 divided by x squared. We saw in example 1 that the integral from -2 to +2 does not converge. It's an infinite area. However, the integral from 1 to infinity, this converges to 1. In some sense, this region is unbounded. It just continues on forever in the positive x direction. We're always adding up some little bit of area as we keep going in the positive x direction. But the value of this area is a finite number. The value of this area is just 1. I think this is really kind of mind-blowing. We can have an unbounded region. In one sense, it seems infinite, but the area of this region is simply 1. Let's take a look at example 3. This seems fairly similar to example 2, and we have the same reason that it's improper. We have an infinite limit of integration. All right, let's work through it right here. Example 3. First thing to do is to replace the problematic limit with a variable name. I'll just use b again. And then we take the limit as b approaches infinity. The antiderivative of 1 over x is the natural log of x. So I have the natural log, absolute value of x, from 1 to b. Everything's positive here, so I really don't need the absolute values. So I plug in the upper limit, plug in the lower limit, take the difference. I have the limit as b approaches infinity of the natural log of b minus the natural log of 1. The natural log of 1 is 0. So I really have the limit as b approaches infinity of the natural log of b. Let's quickly sketch the natural log function so we can evaluate this limit. Natural log function looks something like this. Now, this is a graph that you want to be comfortable with, familiar with. You want to be able to draw this sketch quickly. This is what the natural log function looks like. When x equals 1, natural log of 1 is 0. That's why we had a 0 here. And as x goes out to infinity, the natural log function continues to grow. It grows very slowly. It grows much slower than an exponential or even a polynomial. But the natural log function does trend toward infinity. So as b goes to infinity, natural log of b also goes to infinity. So my answer here is infinity. So to summarize, I would say that the integral from 1 to b of 1 over x dx diverges. It does not converge to a true value. Let's take a look at example 4. For example 4, we have the integral of the natural log function from 0 to 1. And actually, if we look at our little picture here, there's the graph of natural log. The area that we're looking at is this area right here, the integral from 0 to 1. We want to determine whether or not that is a finite area. Now, what's the problem with this integral? Why is this improper? Well, the issue is at 0. Natural log of 0 is undefined. So we have a discontinuity at 0. Let's work through this problem and see if this integral converges. I start by replacing the problematic limit with a variable name. So I'll take the integral from a to 1, and then I need to take the limit as a approaches its true value. A approaches 0, staying on the positive side. So I have this one-sided limit. Now notice we're using limits in two different senses here. We're using limits to talk about the limits of integration, but we're also using limit to denote the regular limit of a function from Calculus 1. So we want to keep straight which limit we're talking about here, because this can get a bit confusing. Now we focus on this definite integral. The antiderivative of the natural log function is x times the natural log of x minus x. We can solve that using integration by parts, but we'll skip over those details here since we've seen that before. There's our antiderivative. We're going to plug in the 1, we plug in the a, and then we take the limit. So I have the limit as a approaches 0 from the right, 1 times the natural log of 1 minus, in parentheses, a times the natural log of a minus a. The natural log of 1 is 0, so I have a 0 here, I have a minus 1 there, and then this minus a I can just replace with a 0. So I have the limit as a approaches 0 from the positive side, negative 1 minus a times the natural log of a minus a, so plus a. Now a goes to 0, so this term just goes to 0. For this term, a times the natural log of a, the a goes to 0. But as a approaches 0, natural log of a goes to negative infinity. So I have an expression of the form 0 times negative infinity. That is an indeterminate form. We cannot evaluate that indeterminate form using regular limit rules. So how do we deal with this? Well, we're going to use L'Hopital's rule. We first need to convert to either 0 over 0 or infinity over infinity, and then we can apply L'Hopital's rule. Let's go ahead and work through those steps. The negative 1 can be taken out in front of the limit since that's just a constant. So I have negative 1 minus the limit as a approaches 0 from the right of a times the natural log of a. Once again, we have a 0 times negative infinity type of a form, so we need to convert to either have 0 over 0 or infinity over infinity. I think it will be most useful to get infinity over infinity, so I'm going to rewrite into a more workable form. I will write this as natural log of a divided by 1 over a. This is equivalent, but now I have natural log of a going off to infinity, and as a goes to 0, 1 over a also goes to infinity. So I have a negative infinity over infinity type of indeterminate form. Once I have the proper type of indeterminate form, I can use L'Hopital's rule to simplify. L'Hopital's rule says take the derivative of the numerator, take the derivative of the denominator, and find the limit of that fraction. So I have negative 1 minus the limit as a approaches 0. The derivative of natural log of a is 1 over a. The derivative of 1 over a, well, that's a to the negative 1. So it would be negative 1 times a to the negative 2, negative 1 over a squared. This is from L'Hopital's rule. Now I have a complex fraction here, fraction over a fraction. I don't like that very much. So when I have a fraction divided by a fraction, I invert the denominator and multiply. So I still have the negative 1 out front minus the limit as a goes to 0 from the right. 1 over a, that was the numerator. I'm going to multiply now by the reciprocal of the denominator. That's how to do fraction division. So times negative a squared divided by 1. There's the reciprocal of the denominator. All right. The a squared cancels with an a, so I have the limit of just a. As a approaches 0, a approaches 0. So this entire limit just resolves to 0. So I have minus 1 minus 0. So the answer is negative 1. As a final conclusion, I write the integral of the natural log from 0 to 1 converges to 1. If we look at the picture once again, here's the graph of the natural log function. It looks something like this. We are finding the area from 0 to 1. That's this unbounded area right here. It turns out that that area has a finite value. The area of that region is 1. And we can find that using improper integrals.